Welcome to this explainer. Look, I'm speaking directly to the technical leaders, plant managers, and procurement directors out there, the ones operating right on the bleeding edge of high-hardness machining. Today, we're taking a highly rigorous, scientifically grounded look into solving the absolute most critical bottlenecks on your production floors. We aren't talking about your standard run-of-the-mill applications today, okay? We're focusing strictly on the extreme end of the spectrum, machining hardened steel up into the HRC65 range, tackling those aggressive high-temperature alloys, and exploring exactly how advanced metallurgical engineering is totally changing the game. Okay, let's dive into this. We're going to follow a highly structured roadmap today to show you some undeniable metallurgical superiority. First, we'll look at the hard machining crisis. Second, metallurgical armor and stability. Third, the legacy of quality control. And fourth, targeted high-hardness solutions. Section 1. The hard machining crisis. Let's establish our baseline here and shift our focus right down into the trenches of hard milling, an environment where standard tooling doesn't just struggle, it outright fails. So I want to pose this question clinically, because if you're overseeing a facility that's machining hardened steels, you already know this visceral pain point. Are unexpected tool stalls crippling your hard milling operations? When you're dealing with extreme cutting scenarios, pushing that HRC55 to 65 range, the margin for error is essentially zero. A tool stall? It isn't just a minor inconvenience. It's a cascading failure that can disrupt your entire production schedule. The physics of this problem are straightforward, but man, they are brutal. Standard tool degradation means the substrates experience rapid thermal deformation. The cutting edge literally loses its physical integrity, and that leads directly to geometric collapse. Contrast that with the extreme cutting demands of HRC60 plus materials. These metals, they do not yield easily. To cut them efficiently, your tool requires absolute geometry stability. It absolutely must maintain its microscopic edge profile under just immense mechanical stress and scorching high heat resistance scenarios. And when that geometry collapses, the costs just skyrocket. You aren't just paying for replacement tools. You're dealing with unexpected tool chipping that embeds microscopic carbide fragments right into your workpiece. You get compromised, shattered surface finishes that fail inspection. You suffer sudden production stalls, which lead to incredibly costly manual rework or, even worse, outright scrap. And when your tool life is unpredictable on high-temp alloys, well, your quoting, your lead times, and your profit margins all become totally unpredictable too. We have got to engineer our way out of this crisis.
Section 2. Metallurgical armor and stability. We're transitioning our narrative down to the molecular level now, signaling a major shift from operational crisis to advanced material science.
And this brilliantly illustrates what we're talking about. Enter polycrystalline cubic boron nitride, or PCBN cutter technology for extreme hardness. When paired with ultra-fine grain cemented carbide substrates, this technology acts as a literal heat shield. We're talking metallurgical armor against abrasive wear. Much like a spacecraft re-entering the atmosphere, your tool needs to survive extreme conditions. PCBN is second only to synthetic diamond in hardness, making it the absolute ultimate substrate for machining hardened carbon tool steels, ball bearing steels, powder metallurgy, and high-temp superalloys.
But hardness alone isn't enough. It's really about thermal survival. 1,300 degrees Celsius. Just let that number sink in for a second. That is the operating temperature resistance of this PCBN technology. Standard carbide binders begin to soften and fail long before this point. But at 1,300 degrees, this extreme thermal stability completely prevents geometric collapse. Whether you're cutting nickel, cobalt, chromium, or iron-based high-temperature alloys, the tool maintains its armor. The heat goes directly into the chip, not the tool, preserving your edge and your pristine surface finish.
Now, what's really interesting here is the hard data. It's undeniable. Let's walk through these parameters. For finished machining on HRC55 and above, we're pushing cutting speeds of 80 meters per minute with a 0.5 millimeter depth of cut at a feed of 0.2 millimeters per rev. Now, for heavy cutting on slightly less hardened steel, HRC55 and below, we're maintaining that exact same 80 meters per minute speed, but dropping the depth of cut to a massive 2.0 millimeters. This proves you absolutely do not have to sacrifice speed or precision when dealing with extreme hardness, provided your metallurgical armor is actually up to the task. Section 3. Legacy of quality control. Of course, brilliant science in the lab really only matters if it can be replicated at scale on your factory floor. So let's shift our focus toward corporate reliability and frame these advanced solutions within a deeply trusted manufacturing heritage. You cannot fake precision manufacturing. It has to be built over time. The engineering legacy we're looking at began in 1998 with the foundation of manufacturing R&D. Moving into the 2010s, there was the integration of advanced CNC grinding and ultra-fine substrate development. And today? That culmination is a full process quality control system specifically calibrated for extreme HRC scenarios. For the procurement directors watching, this right here is your risk mitigation. This level of precision isn't just some happy accident. It's backed by decades of rigorous, standardized quality control. And you can really see the sheer breadth of capability here. It scales all the way from vast arrays of standardized ISO precision inserts, engineered for perfectly repeatable, flawless performance, right alongside highly specialized, custom, non-standard milling tools. I'm talking about tools like polycrystalline diamond or PCD chamfer cutters. These PCD tools are absolutely crucial for removing workpiece edge burrs and achieving those perfect mirror effect finishes, with the tool life extending well into the tens of thousands of pieces. Providing consistent precision and absolute geometry stability for the world's most demanding industrial applications. That really summarizes the overarching corporate commitment to zero-defect manufacturing. When you're supplying tooling for the aerospace, mold-making, or heavy automotive sectors, consistent precision and absolute geometry stability aren't just marketing buzzwords, right? They are the strict requirements for entry. This heritage is fundamentally about building deeply reassuring trust with the plant managers who put their own reputations on the line with every single cycle start. Section 4. Targeted high-hardness solutions. Let's move to our final segment, where we position this comprehensive catalog as the targeted, highly actionable solution to that chipping and stalling crisis we talked about earlier.
So, the crucial point is this. Whatever specific bottleneck you're facing, there is a dedicated, engineered solution ready to deploy. This is the HRC60 Plus arsenal. We have HRC65 solid carbide ball nose end mills for aggressive 3D profiling. We've got TCN and nano blue coated corner radius mills that further enhance heat resistance and lubricity. We've got the PCBN inserts for unyielding hardened steel turning, PCD diamond chamfer cutters for those flawless mirror edges, and advanced U-drill inserts designed to push through punishing alloys. It's a comprehensive readiness for literally any extreme cutting scenario you can throw at it.
The science is clear and the solutions are proven. It is time to upgrade your facility today and eliminate unexpected tool chipping and sudden production stalls for good. I urge the technical leaders and procurement directors tuning in to explore the full HRC60 Plus series directly at www.evergreencarbide.com. Equip your machines with true metallurgical armor. Because I want to leave you with this provocative thought. In an industry where absolute precision and maximum uptime are literally everything, what is settling for standard tooling actually costing your facility? Thank you for joining me for this explainer. I'll catch you on the next one.